Assalamu alaikum. Second part of our lecture 7 is going to start. Uh, we have covered 4 sections of this chapter, section 7.1 up to section 7.4. Let me share with you the screen for chapter 7. So we are talking about digital transmission through additive wide Gaussian noise channel. So let me go to section 7.5 today. Section 7.5 on page 370 is optimum receivers for digitally modulated signal in additive wide Gaussian noise channel. So now we are interested to design optimum receiver for digital modulated signal in additive wide Gaussian noise channel. So let us consider a digital communication system that transmits digital information by use of any of the M-array signal waveforms described in the preceding sections. Thus, the input sequence to the modulator is subdivided into K blocks. The first thing is that we divide the sequence of bits into K bit blocks or symbols. We call them symbols or K bit blocks. And each of the M, which is equal to 2 raised to power K symbols, is associated with the corresponding baseband signal waveforms from the set. So first we define the set of baseband signal waveform, which are called Sm as a function of time, where M goes from 1 to up to M. So this is a set of signals. Each signal waveform is transmitted within the symbol interval or signaling interval or time slot of the duration T. So each symbol is transmitted within the signal interval or symbol interval. To be specific, we consider the transmission of information over the interval 0 to T. The channel is assumed to be corrupt the signal by the addition of white Gaussian noise as shown in figure 7.30. So the model is over here in figure 7.3. You can see that the transmitted signal is Sm of T, then it goes through the channel, noise N of T is added, and received signal is R of T equal to Sm plus noise. So we have already talked about the signal waveforms. Now we are moving towards the receiver side. So the received signal is this thing, Sm plus Nt, where T goes from 0 to T. So what are the properties of noise? Noise N of T denotes the sample function of the additive wide Gaussian noise channel process with spectral density Sn is equal to N0 divided by 2 watts per hertz. So this is a standard spectral density for Gaussian noise process. Based on the observation of R of T over the signal interval, we wish to design a receiver that is optimum in the sense that it minimizes the probability of making an error. So we have to decide, we have to design a receiver. This sentence is very important. We wish to design a receiver that is optimum in the sense that it minimizes the probability of making an error. It is convenient to subdivide the receiver into two parts, the signal demodulator and the detector. Okay, so the receiver has two parts, signal demodulator and detector. The function of the signal demodulator is to convert the received waveform R of T into n-dimensional vector R. So R has components R1, R2 up to Rn, where n is the dimension of the transmitted signal waveforms. We have already seen the dimension of signal waveform. If we have 4 signals, then we have 4 observations. And all those observations are put in a 4-dimensional vector or observation vector R. The function of the detector is to decide which of the m possible signal waveform was transmitted. So first thing is to signal demodulate and then signal detection process. So detector will So there we are receiving so many signals, so the detector has to decide which signal was transmitted. So this is the job of the detector. To realization, now we will talk about signal demodulator. Signal demodulator in section 5.1 and section 5.2. So there are two types of demodulator. One is based on the use of signal correlators. So one thing is called signal correlator. The other type is called mesh filters. So these are very important things: signal correlators and mesh filters. So first we will talk about correlator type demodulators. So section 5.1 will talk about correlator type demodulator. If you can see this figure 7.31, so this is the structure of correlation type demodulators. Okay. So first thing that you should know is, let me show you a diagram from our slides for chapter 7. We have covered slides up to, I think, slide number 56 up to 56. So these are the corresponding slide for section 7.5, optimum receiver for digital modulated signal in AWGN channel. So first thing is that we talk about the receive signal, then the noise and its spectral density. Since noise is a random process, so we have to talk about its spectral density. And then we have an observation vector R, which is n-dimensional. So this is the structure of demodulation and detection process of a digital signal. So this is our demodulator. So the transmitted signal comes at the receiver end, and the transmitted signal is corrupted by noise, AWG, and both are added together, and then RFT is at the input of our receiver. The receiver has two parts: demodulate and sample, and then detect. So this is the detection part, and this is the demodulation part. So it will first of all frequency down conversion. So down conversion means that we may use a carrier frequency or a product demodulators to down convert the frequency, because the input may be at higher frequency. We first down converted, then it is passed through a receiving filter, then an equalizing filter. Equalizer actually is a compensation for the channel induced inter-symbol interference, ISI. So this equalizer is very important part, and Dr. Adnan will be talking about these equalization filters or different types of equalizers. The job of equalizer is to invert the channel-induced inter-symbol interference. So it may happen that one symbol is interfering with another symbol. So we have to compensate those channel-induced ISIs. So equalizer, the job of the equalizer will be to correct those things or remove the inter-symbol interference. Then we will sample it at t equal to t, and then we detect it. The detection device will decide upon the which signal was transmitted. So we will set some threshold, and the received signal will be compared with that threshold, and then a decision will be made that the particular signal waveform was transmitted. Okay. So as I talked about two types of demodulator, one is called correlation type demodulator. So this is the structure of correlation type demodulator. So receive signal is correlated with different basis functions phi1, phi2, phi-n. So then it is integrated and then sampled. So we have R1, R2, Rn. So sample is at time t is equal to capital T. So this is the duration of our symbol. So we will sample it. So this process is called correlation. So R is correlated with phi 1, R is correlated with phi 2, and up to phi n. So we will decide about which observation was coming, and we will be sampling it at t is equal to t. So this is the correlation type demodulator. So mathematically it will look like this, that any rk, k can be 1 up to n, and the received signal will be correlation. This is called correlation, cross correlation. So r of t is multiplied by with this basis function. Basis functions are, you know, that these include the carrier frequencies. So this will be correlated. Then we can put the value of r over here, Sm plus noise into phi of k. So then it will have two terms, Sm and phi k. Sm and phi k, this whole integration can be written as Smk. Smk. And this noise will be correlated with this basis function. So this will be represented as n of k. K can go up to n, 1 up to n. So in metric form or in vector form, this whole process, this whole equation can be written as R. This bold-faced R is equal to Sm plus n. Now let us consider the noise component, representing white noise with orthogonal waveforms. AWGN can be expressed as a linear combination of orthogonal waveforms in the same way as signals. So noise signal can be represented as two components. One is n hat and the other one is n bar. So this thing can be written like this. So this n hat is the projection of noise component on the signal coordinates, phi 1, phi 2, up to phi n. So this noise component can be expressed like this. Okay. Then n bar t is defined as the noise outside of the signal space. So if it is outside the signal space, then there is no correlation. So this cross correlation will be equal to 0. Thus we can express n of t as a vector of its coefficient similar to signal waveforms. So n is now a vector n1, n2 up to nn, where n is a random vector with zero mean and Gaussian distribution. So this is a very standard way of representing noise, that it is a random vector with zero mean and Gaussian distribution, and where the noise components and I are independent. So the mean of the noise process, which is Gaussian, following a Gaussian distribution, is 0, and the variance of noise is given by this expression. Sigma square is equal to variance of noise. So you know variance can be calculated by taking the expectation of this expression and the square of this cross correlation process, nt and phi j. So we are trying to see if there is any correlation between noise and the basis function. So this thing, the variance comes out to be n naught by 2. So if we can put it over here, f of n is equal to product of f n I is equal to 1 to n. Then we can write it as a this expression 1 over pi n naught bracket n naught by 2 e raised to power ni square over n naught. I is equal to 1 to n. Okay. For R of k equal to Smk plus Nk, cause Smk can be viewed as known. Rk is Gaussian random variable with mean Smk. So for the observation vector, which is also following, which is assumed to be Gaussian random variable with mean Smk, and its variance is n naught by 2. Thus we can see the probability density function of the random variable R. So now we want to find this conditional probability density function, that it is a function of R when Sm was transmitted. So it is normally represented like this. So since we have k K components, so they are all multiplied. This is the product. This pi is product multiplication. K equal to 1 up to n, and FRK is given SMK, where FRK SMK is this Gaussian distribution function. So this is normal distribution function or Gaussian type. So it is represented by 1 over pi n naught e raised to power minus RK minus SMK whole square divided by n naught. So in vector form, this can be represented by this expression. So instead of taking R component summation, this k equal to 1 to n, so we will just represent then the boldface R. So this is actually represent RK minus SMK. So this is the vector because it has n components. So this whole expression is in between the exponents. So it is exponent minus this thing. So you can see this expression. So this is a vector notation for the FR given Sn. So this is usually called the likelihood function. FR slash Sn is called the likelihood of Sn vectors. R is sufficient. Vector R is sufficient statistics for reaching a decision on which the M signals was transmitted. So this likelihood function is very important. So it gives us the space where the signal will lie, or it will lie inside this likelihood function, or it will be outside the likelihood function. Okay. Now let us consider an example so you will get the idea of what is going on. Example 7.5. Consider a 2-PAM signal set in which the basic pulse shape G of t is rectangle, as shown in the following figure, this one. So this is the baseband signal. It is between 0 to t and its amplitude is A. Determine the basis function phi of t and the output of the correlation type demodulator. So we want to see what is the output of the correlator type demodulator. So as I've already seen, this is the structure of the correlator. Okay. So from already our knowledge of finding a basis function, we have this expression from Gram-Schmidt orthogonalization. So this is the basis function, or sigma of t, and psi of t, and this is the energy. Energy is a square into t, a square into t. So we should be able to find this energy and the basis function. So if we put the value of g of t over here, so it will be further simplified by 1 over t under, because a square t and this will be cancelled. So we are only left with 1 over t under the root, and it is in between 0 to t. The output of correlation type demodulator is then can be found from this expression: R is equal to R of t into psi of t. So R of t and psi of t will be 1 by under root t over here. So we have to integrate only R of t. R of t is equal to Sm plus noise. This is actually plus symbol over here, not equal. So 0 to t Sm plus noise and t. So 1 by t under the root 0 to t Sm is separated and the noise is separate. So this can be written as Sm plus noise. Sm plus noise. The probability density function for the sample output. Now we have seen in case of PAM signal, we are only transmitting two signals, S1 and S2. So for each of them, we will get this likelihood function by putting the value here, R minus S1 and R minus S2. So these are the two likelihood functions. So they are plotted by like this. So this is the likelihood for S1 and this is the likelihood for S2. So this is the likelihood function. So some of this likelihood of S1 is overlapping with S2. So this is the decision region, this is the boundary, which is actually separating them, these two likelihood function. If a received signal is in this region after this line, this vertical line, then we have a correct detection that S1 was transmitted. Similarly, this is the region for S2. If our observation vector is equal to S2, then it will fall under this graph or this likelihood function. So we will have a correct observation. However, if S1 goes into this region, this line, this region, then there is an error because actually we are transmitting S2, but we have transmitted S1, but we are detecting it as S2. So there is an error. Similarly, S2, if it goes to the region of error. Okay, that was the example for PAM signal section 7.51. Okay, now let us move to our book and see what it shows us in the book. So this is our book part. I think it will have the same thing. Yes, it is almost the same notation and same mathematical form. And this is the likelihood function, Gaussian distribution. Okay, yes. So we have covered up to this point. So example 7.51 was covered here in the slides. PAM signal, you can see all those details we've already discussed, and you are very well familiar with the notation that we are using. Okay, so we have already covered up to this point. Now we move to second type of demodulator, which is called matched filter type demodulator. So match filtering type demodulator. Okay, let me take here a break for a few minutes, then we will come back again.